Good morning and welcome back to the Design of Central AC lectures. This is the fourth lecture in the series. We were discussing in the last few videos about certain concepts which are required for doing a design of Central AC. In the last very video, we talked about the concept of room sensible heat factor. We also talked about the inside design conditions, outside design conditions, how to determine the apparatus dew point and coil capacity in terms of refrigeration. All this we did by using the psychrometric chart and by learning the concept of what is known as room sensible heat factor. In today's video, you would be learning few more interesting concepts. For example, the concept of outside air total heat, grand total heat, and what is known as grand sensible heat factor. Remember, grand sensible heat factor is different from room sensible heat factor, G for grand. All these terms would sound very funny, but they are nevertheless important in the design of AC system. We would also learn how to select the coil apparatus dew point, ADP, using the psychrometric chart and by considering the load with ventilation. Remember, in the last lecture, we talked about the load without ventilation. And for this, the load with ventilation, we would be calculating the grand sensible heat factor. So this is a schematic for better appreciation. Let us say that we are interested in designing a AC system for this room. Step 1 in the design is to select the inside design conditions, Ti, the temperature to be maintained inside, and the relative humidity to be maintained inside, RHI. Then we need to talk about the outside design conditions based on the location, the weather of that place. This schematic is different from the earlier one in the sense that here we are introducing fresh air or ventilation air for air conditioning. So you see that there is a mix of the return air which is from the room and the outside air which is being introduced for freshness. So this return air which is at the state I mixes with the outside air which is at the state O, and this mixing, will assume it as an adiabatic mixing, would result in the new state, state 1. So this state 1 would be of interest for us. The state 1 air would enter the cooling coil, the AC apparatus, and it would get conditioned to the state S. So state 1 would be converted to state S, and this state S is the supply state at which the conditioned air would enter the room, and this conditioned air which is entering this room would overcome what is the sensible load on the room and what is the latent load on the room. Once these loads are overcome, the occupants inside this room would feel comfortable at the temperature Ti and the relative humidity RHI or the specific humidity omega I. How to calculate the sensible load, how to calculate the latent load, that you will learn when we study load calculations in more detail. So when you want to convert this mixed state 1 to the supply state S, so the cooling coil would condition that, and this state 1 to state S is called as a condition line, or it is also called as a grand sensible heat factor line. There has to be certain proportion in which this fresh air and return air has to be mixed. So how much ventilation we need to give? So that would depend upon the application. For example, in operation theaters, we would require more of the fresh air, whereas in the cinema halls, we would require less of the fresh air. So depending upon the application, the ventilation requirements are fixed. And you will find those standards in the handbooks of ASHRAE, ISHRAE and all that. So one S line, that is state 1 to state S line, would overcome the load on this room, and it would also overcome the fresh air load. So this is called as grand sensible heat factor line or process line or condition line. So we'll plot this on the psychrometric chart. So the outside conditions are known, we can plot it on the psychrometric chart. The inside conditions are known, we can plot this on the psychrometric chart, and we can join this line. So the actual condition, which is the condition of entry to the equipment, that is the AC, would not be I, it would not be O, it would be somewhere in between depending upon what is the proportion of ventilation. So we need to look at that point 1. Point 1 is what? It is a point after mixing, which is the entry to the cooling coil. We need to locate the point 1 on this line which we had plotted, that is a line joining point O with point I, the state O with state I. So how to get the state 1? So for getting the state 1, we need to do an energy balance. And what is that energy balance? So energy balance is, as we said, we need to get the state 1. So I need to talk about the energy of the fresh air plus the energy of the return air is equal to the energy of the mixed air. So that is how we calculate the state 1. And energy, how do you calculate? The energy is calculated by the mass into the specific enthalpy difference. So once you do this energy balance, that is mass into delta H plus mass into delta H plus mass into delta H, you will get the unknown, which is state 1. Once you get the state 1, you can locate the state 1 on this psychrometric chart. You can look at the state 1 on the psychrometric chart. How do you look at the state 1 on the psychrometric chart? By knowing the energy of the outside air, by knowing the energy of the inside air, and by knowing the proportion of mixing. If more of the outside air is there, this point 1 would shift towards O. If you don't have any ventilation, zero ventilation, this point 1 would coincide with state I. So the location of I would depend upon the mix of ventilation, how much fresh air we are introducing. Now, how do you calculate the grand sensible heat factor line, and what is that? So for calculating the grand sensible heat factor line, we need to calculate what is known as the outside air sensible heat. It means that how much sensible heat is being contributed by the outside air which is being introduced, the fresh air which is being introduced. Again, it is calculated as the mass flow rate into the enthalpy difference. Similarly, the latent heat is also calculated as mass flow rate into enthalpy difference. So this will be more clear if you take more examples on this. For this present purpose, you just remember that we need to calculate the mass flow rate. Suppose this is, I'm interested in knowing what is the contribution of outside air sensible heat. So for outside air sensible heat, I am interested in these 2 points because these are the points on the temperature line. So get the enthalpy at 1 dash on the psychrometric chart, get the enthalpy at I. This delta H, that is enthalpy at 1 dash and enthalpy at I, would help me calculate what is the outside air sensible heat. Similarly, if I am interested in knowing the latent heat, get the enthalpy at 1 dash and get the enthalpy at state O. So you can read the enthalpy at state O from the psychrometric chart, read the enthalpy at 1 dash, and what you get is the outside air latent heat. That's how you need to calculate the outside air latent heat. The grand sensible heat then can be calculated as room sensible heat plus this outside air sensible heat. So remember this term. Outside air is the fresh air or ventilation air, and room load is what is room sensible heat. So room sensible heat plus outside air sensible heat would be grand sensible heat. Similarly, you had calculated outside air latent heat plus the room latent heat, which is obtained from the load calculations. This 2 would give you what is known as grand latent heat. So remember this, GSH is grand sensible heat, GLH is grand latent heat, and GTH is the grand total heat. So this ratio, the proportion of sensible and the total heat, is captured by grand sensible heat factor. So what is grand sensible heat factor? Grand sensible heat factor is grand sensible heat upon grand sensible heat plus grand latent heat. So we had calculated from the psychrometric chart OASH. RSH is obtained from the load calculation. RLH is obtained from the load calculations. This way we can calculate grand sensible heat and grand latent heat. And by this ratio we get grand sensible heat factor. Once you get grand sensible heat factor, similar to what we had done for RSHF, we now draw a grand sensible heat factor line through the reference circle. Look at this. What I have done? I have drawn a parallel to this grand sensibility factor line, and you get this line 1 to S is parallel drawn using the SHF scale on the alignment circle. So 1 to S is a grand sensible heat factor line. So grand sensible heat factor line would intersect the saturation curve, and that is how you get what is called as the dew point. So this apparatus dew point is obtained this way. So now what is this 1S? 1S is the grand sensible heat factor line. And what is this IS? IS is the room sensible heat factor line. From the psychrometric chart, I can read the value of apparatus dew point. I had calculated the grand total heat. Knowing the apparatus dew point, I can calculate the mass flow rate. So look at this now. So the cooling capacity, that is cooling load, that is grand total heat, is mass into enthalpy at state 1 minus enthalpy at apparatus dew point. So this is the cooling coil capacity in terms of refrigeration. And by knowing this grand total heat and by knowing this enthalpies from the psychrometric chart, you can get the mass flow rate. So that is what is the design. So you can try this example. Design a AC, pause this video, write down these parameters, and using these parameters, this is the grand sensible heat, grand latent heat. The mix is given and 10% of total here. You can do for yourself, please do it and convince yourselves that you can calculate the grand sensible heat factor. You are able to draw the grand sensible heat factor on the psychrometric chart, and by drawing that line, you should be in a position to calculate the apparatus dew point, mass flow rate, and cooling capacity. Please note that without doing this numerical, you won't be able to internalize what you had done. So meet you in the next lecture on the concept of bypass factor, concept of ESHF, and how to design a cooling coil by taking into consideration the bypass factor. Bye for now. Thank you.